In this video, we're going to look at impulse. The definition that the book gives is that the impulse, I, is equal to, and that's a vector, the force times delta t. That's not really the correct total definition, but it'll kind of work. It is related in some way that the force times the time of interaction causes a change in linear momentum, and that's called the impulse. A better way would be to look at it in terms of a force time diagram, that is the graphical interpretation. And because it's a vector, it of course could have graphs of the x component of the force, the y component of the force, etc. And what we mean by this is that there can be some force. Maybe the components look maybe like this. And what you're doing here is you're taking some height, fx, at that time, and you're taking some width, delta t. And then you can think that there's another piece of impulse right next to it, which has another value of xx. And likewise, you can continue doing this on and on, adding up these little, whoops, I left that one a little low, till you add up all the area under the curve. And this would give you the x component of the impulse. If you did the same thing of finding the area under the curve here, you get the y component of the impulse. So impulse is a vector, and it's related to summing up the little areas under the force time diagram. So I put that under graphical interpretation. It is the area under a force time graph. Now be careful, it's force time. Force displacement, the area under it gives you work. Force time, the area under it gives you impulse. Now what we're going to do with this is we're going to connect this back to Newton's second law. Okay, so let me draw you one more of these diagrams. Area is impulse. So I probably drew you more diagrams than you wanted. Now, this is a non-calculus based course, and as a non-calculus based course, we don't actually do the calculus to get out of it. But if this force was the net external force, if that's what you had the net external force, and you summed that by delta t, and you found the area under that curve by summing up the little rectangles, what you would find, the most important thing, is that this impulse is not just some arbitrary value. This impulse is exactly the change in the linear momentum. This is Newton's second law. Remember, Newton's second law says the sum of the external forces is equal to delta p over delta t. And I've left out the little limit for now. Then if you bring the delta t to this side, which is the impulse, then that's equal to the change in p. Now, you might ask, why do we ever do this? Why don't we find the forces, we're going to add it up? In the real world, the answer is that's not what you're doing. In the real world, in things like collisions, explosions, and such, it turns out that forces change dramatically. They're not constant. They vary a lot. And they occur over such a short time period, it's impossible to measure them. So, for instance, I was drawing very large graphs. What it probably looks like in the real world is something like this. Or something like, it's not a very good drawing. So this time is really short. It may be a billionth of a second. It may be less than a billionth of a second. So there is no way to get a watch and measure this time, or have any instrument that's fast enough to measure the individual F. So you can't measure this, and you don't have an ability to measure this, but you may be able to measure this. So you can't tell me what the force is, and you can't tell me what the time is, but you can tell me the change in P, because you can measure the mass of the object and its velocity before and after the process. So what you're able to measure, in effect, is this thing called the impulse. And so especially in engineering applications, they talk about impulsive forces in collisions, hammers hitting things. What they mean is they're able to measure the area under the curve, but they're not able to measure the height or width of the curve by itself. Now, we can do more to this. There are certain graphs that we can know a lot about. For instance, if the graph was like this, and it was constant, when you have a constant graph, that's by definition what you call the average. So if you talk about the impulse having a particular area under the curve, what we mean is that if you had this graph over some time, let's say this much time, whatever that is, which is the same as this time right here, there's a certain amount of area here. Maybe that is 10 newtons times the second. And there's the same amount of area here, 10 newtons per second. And all you can measure, for instance, the impulse is the area under the curve. I can talk about making it a rectangle, an average force times a time. There's delta T, there's the average force. And that will give me the same value of I as maybe the real force, which is much larger, but occurred under a rapidly differing time. So a lot of times I can't tell you the shape of this, so what I talk about is what it would be like if you had a rectangle. How big would the average force be over what time? When you do that, and you're taking the delta P and relating it to F, what you're doing is the average force. Now here's the danger of that in the real world. In things like car crashes, you can compute the average force. You can find the delta P here. You know how big the car is, how much its velocity is. Then it hits the wall. You know the mass of the car, and you know its velocity is now 0. You can calculate delta P. Maybe you can find out that the time occurred of the collision in 1,000th of a second. You can divide delta P by delta T and find this force. But that force is the average force. What will determine whether you survive is not the average force. It'll be the max force. So while the average force may be survivable down here, the max force might be too great and would kill you. Now we can do some things. We can use dummies in car collisions, and we can set them so that if a force exceeds a certain value, for instance their head falls forward or something else, and you try to get us some idea of what the maximum force is. And that'll get us some ability of survivability. But it's still useful to take this formula and look at what will happen in terms of delta T as you change delta T, if you make it smaller or you make it bigger. So the formula has some use, but it could be that the forces on your body would be greater than just this average, F average. So let's talk about this. You can have two graphs that are equivalent in change in linear momentum. That is, they have the same impulse, but they don't have the same force structure. This can be greatly important in things where things happen quickly. For example, it can be important in the operation of seatbelts, airbags, catching baseballs and footballs, karate chops, and boxing punches. In each case, the change in linear momentum is the same. It's fixed. But the force required to produce it can be radically different. And I'll show you that in the graph. Let's see what I put here. The force required to produce this change Depends dramatically on the interaction time. This is one of the cool things in physics. For instance, you might have a very small force over a long time. And inside of this, you might have 100 units of area. That's delta P. So 100 seconds, 1 Newton force equal 100 Newton sec. Long time, small force. On the other hand, you can get 100 Newton seconds doing it like this. .1 second, 1,000 Newton force. 100 Newton sec equal delta P. Large force, small time. If you're trying to bust something, like a karate chop or quick hit on a baseball, you want a short interaction time, it produces a terribly large force. On the other hand, if you want to survive a car crash, if you want to catch a football when it's thrown to you, you want to make the interaction time long so the force required to do it is small. So a seatbelt simply slows your body over a long period of time. The car zones in the car give way and slow over a long period of time. The airbag flies out and then begins to leak out so that you fall into it and are slowed over a long period of time. Anything that increases the interaction time decreases the force. When you jump and land on your feet, your knees bend. This increases the time and decreases the force. So, seat belts, airbags, all of these safety devices are simply time extenders. All right, we'll talk about conservation of linear momentum in the next video.